Hello everyone. Today we'll be discussing about impulse and ramp response of first order system. The learning outcome of today's lesson is to understand the impulse and ramp response of a first order system. That means with impulse input and ramp input, how the system would respond, of how a first order system would respond, that we are going to analyze today. So in last class, what we discussed? In last class, we discussed about step response of a first order system, how a system behaves for a step input. That is being discussed in last class. Today we'll be discussing the same analysis of first order system, but due to some different inputs, impulse input and ramp input. In addition to that, we'll also be discussing about step response of a first order system with zeros. In last class, we discussed about step response of a first order system having only poles. If a system is having zero, then how step response would be analyzed, that we'll be discussing. Step response of a first order system with delay we also will be discussing. If a system is introduced with some delay, then how the response will be changing, that will be discussed in today's class. So let us start with impulse response of a first order system. Impulse response of a first order system means how the system would respond due to application of impulse input. So this is a first order overall transfer function of first order system in which an impulse input is applied. This is unit impulse, and due to application of this unit impulse input, it will produce an output. So the nature of output with respect to time will be analyzed now. So for unit impulse input, as you all know, the Laplace transformation of unit impulse function will be 1. So the transfer function Cs by Rs equals to this. As Rs is 1, so Cs will become this. Now, here by performing inverse Laplace transformation, it's a simple inverse Laplace transformation involved here. So by performing that inverse Laplace transformation, we'll get this equation. Based on this equation, we can analyze how the system would behave for unit impulse input. Consider a system with a gain of 3 and time constant t as 2. For this system having 3 gain and 2 time constant, the system response will be of this nature. So from this equation, we can say it's an exponentially decaying equation. So the graph is exponentially decaying. Clear? Now, at t equals to 0, when time equals to 0, e to the power 0 is 1. So k by t will be the magnitude of ct. So at time t equals to 0, at this point of time, this is time axis and this is magnitude axis. So at this point of time, at 0 time, the output will be k by t. So k is 3, t is 2. So output is 1.5. Clear? Now, as time approaches infinity, after a long time, what will happen? When t tends to infinity, this ct will become 0. So suppose a very short duration pulse is applied to a system. The system output will be very high, and gradually as time goes on, the output will be decreasing slowly. Just try to remember discharging of RC series circuit. When there is a huge voltage across the RC series circuit applied, capacitor will be charged initially to a constant value, and then when the switch is withdrawn, there is no voltage source connected with the RC combination, the capacitor will discharge it through the resistor and it will be of exponentially decaying curve as shown here. So this is impulse response of a first order system. Now what is ramp response? So for ramp response, what is the change to be made? The input should be changed. The for unit ramp input, Laplace transformation will be 1 by s square. So CS will consequently be the transfer function k by st plus 1 into 1 by s square. By performing inverse Laplace transformation, we'll get this equation. Now based on this equation, we'll analyze how system output CT is changing with time. So this is the equation for output due to application of ramp input. This blue straight line shows unit ramp input having slope of 1. So whenever unit ramp input is applied to a system, it is desired that the output will follow this ramp function, but somehow output follows this green line. Okay. So there is a deviation between desired response and actual response. The desired response is the blue and actual response is the green. Now, why this deviates? Why this green deviates from the desired blue? Because of this term. Okay. Now see here, when t equals to 0, when t equals to 0, this response curve will have no value. This e to the power 0 is 1. So t e to the power minus t by t will be plus t. So plus t minus t will be cancelled. And as t is 0, so kt will be 0. So entire ct will become 0 at t equals to 0. Now, when t is increasing, as the time is increasing, see this gap what is this gap? This gap is known as the error. As mentioned here, this gap is known as error. So what should be the error? This is following, this green is blue is following kt equation, and this is following this equation. So the deviation is of minus t, okay, plus this amount. Now as time approaches infinity, what will happen? When t tends to infinity, e to the power minus infinity will be 0. So this term will become 0. So the deviation will become t. Now when time is less than infinity, say there is some time of 1. So it will be e to the power minus 1. So t to the power minus 1 will have some value which will be added with this. Okay. So the difference will be increasing as time goes on. So initially this difference is less. As this term is less, as the time goes on, this difference will become more, and finally the difference when time tends to infinity will become equals to, this difference will become equals to capital T. Okay. Now this is the ramp response of a first order system. Okay. Now let us discuss what happens if a system is having a 0 term, that is a numerator term associated with s. Along with that, if the system is having a pole. See, GS equals to this, where S equals to minus 1 by alpha is location of 0, and S equals to minus 1 by T, location of pole. So how these zeros poles location are found, that we discussed earlier in basic introductory classes of control system. So the 0 is 1 by alpha minus of, and pole is minus of 1 by T. CS equals to RS into the transfer function. So the RS will be 1 by S for step input. By taking inverse Laplace transformation, we'll get this equation. Now, what this equation signifies? We know this equation we derived in last class. This equation we derived in last class. This is the equation for a first order system with step input. So this is step response of a first order system having no zeros, only one pole. This is step response of a first order system with a 0 and a pole. So what's the difference between these two? If we can differentiate these two equations, then we can understand what's the effect of 0 to the system response. So see, this K term is there. Okay. And what about this part? See, K by T minus of K by T, T will be cancelled. So minus K e to the power minus T by T. This term is also there. But due to presence of this alpha in the numerator part or 0 part, this additional part is being introduced. So a new term we are getting due to presence of alpha is this. This is the new term introduced at the output due to introduction of 0 term. So what is location of 0? Minus 1 by alpha. That alpha part appears here. Okay. Now, it is very clear that if alpha is less than T, then what will happen? If alpha is less than T or T is greater than alpha, the shape of step response is approximately same with offset added by 0. So this 0 term will add an offset of K by T alpha e to the power minus T by T. So e to the power minus T by T will always be there. So K by T alpha is an offset which will be added to the system due to application of addition of 0 term. For T less than alpha, we'll get another response curve. That will be, this will be discussing in next few slides with the help of some examples. Okay, let us consider this example here. Here, GS is given 3 by 2s plus 1. It's a first order system as highest power of s in the denominator of the transfer function is 1. What would be impulse response of the system? Here k equals to 3, t equals to 1 if it is compared with k by st plus 1. So we know the output equation for unit impulse function is ct equals to k by t to the power minus t by tau. So exponentially decaying curve will be obtaining, and the initial magnitude will be k by t, that is 3 by 2, that is 1.5. So this is very simple. Now let's consider this case. For this general transfer function, if k equals to 1 and t equals to 1, what would be response curve? See, this blue line shows the input, unit ramp input, and this green line shows the actual output, and difference between these two is error. Okay, now when t equals to 1, this error will not be very much. If t increases, as we discussed, at the end the final error will be t. So if t is less, error will be less. So difference or gapping between these two will be very less. But let us consider the next example. Here see, t is large, t is 3. So this difference deviation is much larger. So in order to reduce error of a first order system due to application of ramp input, the system time constant should be as low as possible. Okay. Now let us consider this case. Here a system is given with a 0 term. Okay. Now, as we derived the expression for CT for a system with 0 pole both the terms, similarly you can derive this equation, this expression for output, where CT equals to this. Now, the general expression was CS by RS equals to K into 1 plus alpha S divided by ST plus 1. So by comparing with general equation, K equals to 10, alpha equals to 2, and T equals to 3. So this clearly shows T is greater than alpha. So if T is greater than alpha, then what will happen? This is the general expression for output which we derived in few slides back. Now, based on this equation, based on this general expression, substitute the values of K, T, and alpha, you will get this output. Okay. Now, this is the step response curve. Can you find any difference in this step response with the step response of a system having no zeros, which was discussed in last class? Yes, there is one difference. What is the difference? Difference is indicated by this circle. So why this happens? This circle is having somewhat a value between 6.5 and 7. So what is happening actually? For step response of a system with no zeros is K into when t equals to 0, e to the power 0 will be 1. So Ct is 0. So when there is no 0 involved in the system, in the first order system, the response will be like this. But due to presence of this 0 term, the response is starting from a magnitude of 6.7 around. So there is an offset in magnitude. This is the offset. So what that offset is? If we write this equation in this manner, See, this equation can be simplified as this. Now, this part is same as the expression of CT with only poles. This part is the additional part which is being added to the CT expression due to addition of this zero term. Now, here K is 10, T is 3. So 10 by 3 is what? 10 by 3 is 3.33. Okay. Now, what is alpha? Alpha is 2. So 3.33 into 2, 6.67. At t equals to 0, this term will become 1. This term will become 1. So at t equals to 0, the offset will be k by t into alpha, where k is 10, alpha is 2, so 20 by 3, that is 6.67. So this magnitude is 6.67, which is added to the system due to application of this zero term. Clear? Next, if a system is having a transfer function of this, here what's the change? In last case, the system had a transfer function of this where t was 3 and alpha was 2. Now alpha is 2 but t is 1.5. So if t is less than 2, what will happen? As t is less than 2, so this term will become positive. Okay. So as this term becomes positive, this entire term will become exponentially decaying. Okay. So at t equals to 0, this term will become 1. Okay. As this term becomes 1, so k by t, k is 10, t is 1.5. So 20 by 3. Okay. Now what will happen? This 13.33, let me take the values. K is 10 plus k by t. K is what? 10 by 1.5, that is 20 by 3. Alpha is 2 and t is 1.5. So into 0.5, that is half. At t equals to 0, this term will become 1. So this will become 20 by 6, that is 3.33, 13.33. So CT will become 13.33 at the starting, and as time goes on, due to this term, this is exponentially decaying term, so it will be decaying slowly. So if time constant t less than alpha, then the step response curve will be exponentially decaying. If time constant is greater than alpha, then it will be exponentially increasing. So this shows exponentially decaying when t less than alpha. This shows exponentially increasing with t greater than alpha. In both cases, there are some offsets. How to measure these offsets, that we already discussed. Now, this is a system response if delay is introduced to the system. Delay means nothing, but as you all know, ut this is waveform for ut. Now what should be waveform for a delayed unit step function? It is very well known to you all. That means in case of delayed step input, the input will be applied after some delay, certain delay. This delay is denoted by TD here. So as a consequence, the output will also be delayed. Okay. Now the remaining part is same. Due to this delay, there is 2 seconds delay. The step response will be like this. Okay. Okay. So what we discussed today, let me summarize. First, we discussed the impulse response of a first order system. That means how a first order system should behave due to application of unit impulse input. Then we discussed about step response of a first order system, ramp response of a first order system. That means how the system should behave due to application of ramp input. Next, we discussed about first order system step response if the first order system is having some zero introduced to the transfer function or introduced to the system. 2 cases we discussed. In that case, we solved some numericals. We discussed about step response of a system with some delay. So in next class, we'll move towards analysis of second order system. So as of now, I'm ending up here. Meet you all in next class. Thank you.